Okay. Now at least we'll have two separate recordings, one for each class.
That took me
1, 2, 3, 1, 2, 3. Yep, everybody's signed in. Yep. All right. Just, yay, somebody else showed up. Sign-in sheet's there. No, right there by my book. 4 pieces of wire. They're all copper. Which one would oppose the most, which one would let the most electric current flow? Which one? D. You said C? Which one would let the most electric current flow through? You going with D? You're going with B or D?
It's got less length and it's got more area.
All right. Remember your guesses. We'll get back to it. Which one, have you signed in? Yeah? Okay. Which one of you can tell me the significance of this number? .241 times 10 to the power of 18. Avogadro's number? Yeah, no, not it. Yep. Now this is a brave soul parading in front of me with a big old giant Rice Krispie treat. If I wasn't old and fat, we might. Now, 6.241 times 10 to the power of 18. Anybody have a guess what that number means? What's the significance of that number? I know you do because we've talked about it, so shut up. Anyone have a guess? Okay, punch it into your calculator. Everybody got it punched in? Everybody get it punched in. We'll wait. Everybody good? All right, now hit your reciprocal key. What's the reciprocal of this number? Say again? Anybody get a result? You got 1.602 times 10 to the minus 19. Does anyone recognize that number? What is this number? So its unit would be coulombs per electron. Well, then what would the reciprocal of that number be? Electrons per coulomb. This is how many electrons have to flow past a given point in a wire to produce 1 amp of current. 1 amp is, by definition, is 1 coulomb per second. So if you are pushing 6.241 times 10 to the 18 electrons past a point in a wire every second, then you're pushing 1 amp of current. And that's where we're headed. Now, how do we get there from here? Who can tell me about Mary Shelley? Does anyone know who Mary Shelley was? Nobody has a guess. Mary Shelley wrote a very famous novel, The Modern Prometheus, or Frankenstein. Because back in those days, whatever years those were, I don't remember, 1700s, 1800s, long time ago, long before even I was born, scientists were frantically looking for something that they called life force. What gives living creatures life? And Mary Shelley wrote a famous novel about a doctor named Frankenstein who was searching for that very thing, and it was actually a cautionary tale of what happens if he found it. And he produced the monster that people erroneously call Frankenstein. It's, just for the record, the monster is not Frankenstein. Frankenstein is the doctor who created the monster. But he did it looking for something called life force. Now that was in fiction. But in reality, scientists were actually looking for that very thing. And in the process discovered some early developments in electricity. In particular, this one scientist named Galvani, and you may recognize the name, or at least the root of the name, because from Galvani we get galvanic response, we get the galvanometer, and we're going to be using one. We've used one already when we were looking for equipotential surfaces or equipotential lines. We're going to be using one again this week in lab when we set up a Wheatstone bridge. So look at this. What Galvani did was he plugged some metal probes into a frog's leg and found out that when he used these two different metal strips and he plugged them into the frog's leg, he could make it twitch. And he published a paper on it, and he thought that he had discovered that mysterious life force that everyone was searching for. He hadn't actually done that, but he did do some other things that were pretty cool, so we still remember him. One of his contemporaries was a fellow named Volta. Volta was very skeptical of Galvani's work and said, I don't think it has anything to do with the frog leg, the animal tissue. I think it has to do with the fact that you have dissimilar metals. How many of you are in instrumentation? All of you. What do you get when you put two dissimilar metals together? You ever used a thermocouple? Next semester you'll use thermocouples? Okay, well, don't let me, spoiler alert. A thermocouple works on dissimilar metals. You put two dissimilar metals together into contact, and in fact you weld them together to make a thermocouple. At the interface between the two dissimilar metals, a small potential difference will form. And we're not going to worry about the mechanism of how that happens, but it does. And the amount of that potential is very critically dependent upon the temperature that those two metals are at. Okay? And thermocouples are a whole lot more complex than just what I'm telling you here, but that's basically what happens. You put two dissimilar metals together, a very, very tiny voltage is developed, and you can measure that voltage, and it will correlate very precisely with temperature. So as temperature goes up, that little voltage will go up. Temperature goes down, it'll go down. They have different kinds of thermocouples made out of different pairs of metals for different temperature ranges. That derives from Volta's work. I don't know if any of you remember this. I don't guess any of you were old enough to have been around at the time, but back in the 1970s, and much as is happening today, price of copper got very expensive. So people in building industries and the construction industries said, hey, we can hold down costs if we stop pulling copper wire in these houses and start putting in aluminum wire. Great. It's a lot cheaper. Aluminum's a great conductor, just like copper. But then all those houses started burning down. And the insurance companies started getting real upset and started looking into why. The same mechanism. They were still hooking those same aluminum wires to the same terminals that still had copper terminals. The dissimilar metals would produce a voltage, a very small potential difference, but a potential nonetheless. What happens when you produce a potential difference? You start getting chemical reactions. Oxides start to form and to build up and increase resistivity. As the resistivity at the interface between the aluminum wire and the copper terminals started to increase, more voltage was dropped across that oxide layer, more voltage pushing current through, dissipating more and more power until the heat built up and things started catching fire. They found out that they in fact could use aluminum and interface it to copper, but in order to do so they had to use these very expensive hydraulic presses that they could take out and squeeze the wires together so hard and so tight that they physically welded together. And they found out that, well, you know what, copper's gone back down in price, we'll just stop using aluminum wire. Of course, now copper's gone back up. Copper thieves are stealing wire out of light posts in Tulsa, and so what's Tulsa do to respond? They start putting in aluminum wire. Hopefully they're doing it well and doing it correctly, or they're going to start having lampposts catching fire. But that's another story and not something that they asked me about before they did it. So, what did Volta do? He found that with dissimilar metals, you get a potential difference built up where they contact, where they meet. And he cataloged and labeled different potentials that formed between different metals. He found that you could replace any of the metals with carbon and it would work just fine. He built up these tables of potential differences with different types of metals that chemists and engineers still use today. But he did one thing that was just really important. He took one of those pairs of dissimilar metals and he laid them between a rag that was wet with salt solution. He also did it with different acids, but when he did that, he found that it greatly enhanced the potential that would build up. And then he put another one on top, and another one on top of that, and another one on top of that, and he built up this stack of them. You might recognize the schematic symbol. What is that? It's a battery. In fact, it's a 1, 2, 3, 4, 5, 6, 7, 8, 9 cell battery. You go to the store to buy batteries, you buy what? B cells or C cells or AA cells. Because each one of those is not a battery, it's just a cell. It only becomes a battery when you stack two or more of them together. When Volta did this, he found out that the potential from here to here greatly increased. That he could just add all of these little potentials together, and he got it built up. He built up enough that when he touched the two terminals together, he created a spark. And that was a big deal at the time. He created the first battery in modern day. There's actually some argument about whether or not he created the first one. There are artifacts that have been excavated from ancient Egypt that look like they were, in fact, ancient batteries that they used even for like gold plate, electroplating, and that sort of thing. So, but as far as we know, Volta was the first person to create a battery in modern day times, and he's the one we recognize, and that's why we call it a volt, after him. So, this is how you take cells and put them together to make batteries. When you put all of these cells together and you get a potential difference across them, you can then use that potential difference to push an electric current through a conductor or a resistor or a transistor or whatever, a frog's leg. I suggest you kill the frog first. I don't guess any of you have ever gone frogging. You have? By hand or with a gig? My first alligator encounter was when I was frogging by hand. It was a frightening moment. Needless to say, I did an about face abruptly. And with nothing but a paddle and a 12-foot aluminum boat, I outran a 5-horsepower outboard motor through 3 turns of the bayou. Yeah, I saw those big old giant red eyes glowing, and I reached over the bow as I paddled up, and then all of a sudden, whoom, and there was these big giant sets of pearly whites. Whoop, nope, I'm out. Bye. I'm out of here. Moral of the story, when you're frogging, green means go, red means stop. You see the frog's eyes, they're green. If you see red eyes, that ain't a frog. Leave it alone. Yep, I know. That has nothing to do with physics, but it's still fun. What happens when you put a resistor between here? How much current flows? Thank you. The current is V divided by R. What are the units of current? Amps. What's the definition of 1 amp? 1 coulomb per second. What are the units of resistance? Which one of these wires would produce the least resistance? You say this one? D. Why? It's a bigger wire. It has the biggest cross-sectional area, but it also has the shortest length. The resistivity of all 4 of these is exactly the same because they're all copper. But in order to convert resistivity into resistance, you have to consider the area and the length. The longer a wire of any given cross-sectional area, the more resistance it has. I think surely they put the formula in here. There it is. R rho L over D or D over L? Area, yeah, not D. Area. 508. It's equation 18.3, resistivity. And here on table 18.1 is a list of various conductors and semiconductors and dielectrics or insulators and their associated resistivities. Its rho is not a constant. Rho is the resistivity. Yeah, see, on the same page, 508, table 18.1. Gives you all the resistivities for all these different materials. What do you notice about that? Okay. Look at the materials involved. How many of you knew that the best conductor we know of as far as metals in the, at least, not avoiding exotic things like superconductivity and stuff, but just straight up go down to the shop and buy some metal. The best conductor is silver. Very expensive. What else? Yeah. Why would copper, aside from inexpensive, why would copper be a better conductor than silver? Yeah, and they're both kind of malleable. And
I do know copper has, in its valence scale, it actually has an electron elevated to the next level and leaves a spot on one of the sides. I don't remember exactly. I just read the whole row of copper, like chromium.
Right. How many of you have ever polished silver? It does. and I'm not, you know what? Don't quote me on this if a chemist ever argues about it. But my understanding is that with copper, it'll form an oxide layer just like silver will. But the copper will build up, it will not oxidize as much before it reaches equilibrium. You'll lose more to oxidation with silver. Bottom line is, silver is so much more expensive than copper that any other considerations become moot anyway. So.
Best Buy, and they had some speakers there, and I was looking at them, and I looked at the price, and these two towers, they're like 30,000, and then I looked down on it, and it said wiring kit on it, $10,000. And I asked the guy, I was like, so why is the wiring so expensive? He said it's all silver. I don't know, I was just amazed that it was $30,000 for a pair of speakers.
Yeah, not my dollar, not 30,000 of my dollars. I don't care how good they sound. They do not sound that good. Yeah. How many of you have ever heard of people bragging about their electrical contacts being gold plated? Say again? Yeah. Why do they do that? But why would you plate a contact with gold? Exactly, because gold does not oxidize. You have gold contacts, they're going to make good contact every time. That actually copper is actually a better conductor than gold. But because gold won't oxidize, it makes for a great contact. It will always make good electrical contact. That's why NASA gold plates everything. Any contacts that make and break on any space vehicle must be gold plated for that very reason. You spend millions of dollars on a probe and send it all the way to the outer reaches of the solar system and start trying to take pictures of a planet as it passes by. You don't want that to, that switch, it has to work that time. It doesn't matter if it's been sitting idle for 20 years. When they push the button and that contact closes, it has to make contact. If it's been oxidizing for 20 years, what are the chances? Airbags in your car, the same thing. They make a point of gold plating the contacts on your airbag. Hopefully, that thing is going to sit there for 20 years and never do anything. But in that microsecond when it counts, that contact has to make good contact. That's why you gold plate. In point of fact, if you get into this in your electronics, you're going to find that when you do gold-plated contacts, before you gold plate them, you first have to nickel plate them. Because the gold is so soft and malleable that if you just... You have to nickel plate them first to put a solid base under the gold so it'll hold. It's not cheap, but it's not really that expensive. It's not 30,000 expensive. You could set up and do gold plating at your house if you wanted to. I do copper plating when I do through holes on my circuit boards. It's not cheap, but it's not cheap because I had to buy so much of the solution. That's the expensive part. If you're doing small pieces, little bitty amount of solution, small power supply, no big deal. But if you're doing a large panel, then you need lots of amps, even though you don't need that much voltage, because you have to have so many amps per unit area of board or of panel that you're plating. Let's try to get this boat back on course. You'll notice that aluminum is still a good conductor. It's not as good as copper, but it's still a good conductor. Now, So you have the resistivity of a material. You take the cross-sectional area of the wire, or you divide the length by the cross-sectional area, multiply by the resistivity, and you get the resistance in ohms. You'll notice that as area gets bigger, you have more room for electrons to push through, resistance goes down. As area gets smaller, you have less room for the same number of electrons to push through, the resistance goes up. If you take that same piece of wire, make it short, you get a little bitty tiny resistance. You stretch it out longer, and the resistance goes up. So, he was right. Largest area, shortest length, this is the least resistance. Lowest area, the smallest area, the longest length, this one has the highest resistance. A would stop the most current from flowing, would provide the least amount of current. D would provide the most. You'll notice also on this table, they give you temperature coefficients. This gets kind of complicated because if you want to calculate the resistivity of a particular material at a particular temperature, look at 18.4 on page 509. What you have to calculate is the resistivity at a temperature. And let's see, write out the equation. You start with rho sub naught, you multiply by 1 plus alpha times temperature minus T sub naught. Now, T sub naught is a reference temperature. Kind of initial, it's like the initial temperature.
Will that be given?
Well, I wouldn't count on seeing any of this. If you have, it may show up in a homework problem, but it is a homework problem? Okay. Anyway, you have rho sub naught is the resistivity at T sub naught, which is your reference temperature. And then from that, you would then go to the temperature that you're interested in finding out here. Alpha is a coefficient from the table on the previous page. So that right-hand coefficient, it's in 1 over degree C, or per degree C. So it's how much the resistivity changes for every degree C it goes up or down. Now these, generally I think, yeah, in fact here it tells you that these are reference temperatures at 20 degrees C. So if you were going to use this in an equation, you would have to use 20 degrees C as your T sub naught, or rho sub naught. I take it you're all well versed in Ohm's law, at least the scalar form of it here. You know how to manipulate it. Go from IR equals V. R equals V over I. If you're given voltage and current, you can find the resistance. Who can tell me the formula for power? I always like to start with pi, or where E is actually V. And so I learned Ohm's law as I equals E over R, where E was electromotive force, but I don't want to confuse it with the E field. So, and again, voltage is IR, so that could be changed to I times IR, or I squared R. I is V over R, so it could be changed to V over R times V, or V squared R. But what is power? When you talk about the power, electrical power, what units are you using? Watts. What is a watt? I think it is. Or a joule per second, right? So, question we talked about the other day. When your electric company bills you for the electricity you used, what do they charge you for? Kilowatt hours. Or every 1,000 watts for 1 hour is a kilowatt hour. Remember how we used that funny unit of energy called an EV? That was actually equivalent to some number of joules, 1.6022 times 10 to the minus 19 joules. Kilowatt hour, well, this is basically a watt times time. So just like the EV, the kilowatt hour actually reduces to just a number of joules. Total amount of energy you've used. Okay? The kilowatt, that just means thousands of watts. An hour can reduce to seconds, so you could actually convert kilowatt hours into watt seconds, or which would in fact be joules. And actually, you know what that means, fellas? That means we are now actually into next week's first lecture. So, stop taking notes now and start asking questions. Who has questions?
really familiar. Come back from ACDC or ACDC 1 and ACDC 2.
Yeah. Yeah, this has actually been looking forward to getting to this point because now it's all of it will start to make more sense to you. It will start coming into context. But we've got time, so don't pack up too fast. Let's keep talking. We don't have to keep covering new material. We can talk about the existing material. Get y'all to thinking a little bit. You've got a conductor, a wire, and you're pushing current through it. What is actually pushing the current? Why is it called a conductor? You've got an electric wire this is just a chunk of wire. And it's connected to a circuit with a light bulb on one end and a switch and a breaker panel on the other, or a battery or whatever. But it's part of a circuit, and you're pushing electric current through here. Just a piece of bare exposed wire, amp, milliamp, doesn't matter. You've got current flowing through it. You take out your voltmeter probes. You touch that wire here with one voltmeter probe, and you touch it here with the other voltmeter probe. How much voltage are you going to measure?
Wire itself.
Yeah. 0 volts. Is that actually the true value? It's close. For practical purposes, it is. But we also know that this wire is not 0 ohms. If it were 0 ohms, how many volts would it take to produce an amp of current? No. 1 volt will produce 1 amp through 1 ohm of resistance. What happens if this actually went to 0 ohms of resistance? Well, you would get, in the limit that the resistance goes to 0, the current would tend towards infinity with 0 volts applied. That is not as physically nonsensical as you would think. Remember our equipotential surfaces, our equipotential lines? What is the definition of an equipotential? And this is going to come up again in lab this week when we do the Wheatstone Bridge. When things are at equal potentials, it takes 0 work to move an electron between any 2 points on that line. It also means that if the 2 points are at the same potential, there is no current is going to flow. Right? We say this is a conductor. What we're actually saying is that the resistance is so tiny that we can ignore it. When we start analyzing the circuit, we can consider all of the voltage developed over here at this battery as being developed across this resistor. And none of it in the wire. That's what we're saying. We're saying that any voltage that is developed across that wire is trivial and insignificant. But is that always true? What happens if you push 100 amps through 18 gauge Romex. It catches fire. Because all of a sudden the voltage developed across this wire is not trivial. And when you're developing voltage and you're pushing current, you're dissipating energy. You're turning energy into heat. Plastic melts and buildings burn because it does not go to 0 ohms. As long as you keep the current low enough, then you can consider the potential drop across here as 0. But the resistance is never actually 0. Anybody have any more thoughts? Comments? Questions? No? What about you? Well, hopefully y'all have some thoughts at least. But, huh? It is a Friday, ain't it? It's a Friday on a brand new month. Y'all go. See you next week.